Welcome, ladies and gentlemen, here at the Technical Forum at the group exhibit Hydrogen Fuel Cells, and for the first time this year in Hanover with batteries. Come in, have a drink on the house, and enjoy with me our next presentation dealing with the topic the DCODE project, online diagnostic of PEMFC by electrochemical spectroscopy thanks to the power converter. And the presentation will be the DCODE project coordinator, Cesare Pianese. Give him a big hand, please.
Thank you. Thank you. Welcome to my presentation. This is a project that has been funded by the European Commission through the joint undertaking. And the title is DC-DC converter-based diagnostics for PEM fuel cell systems. And it deals with the diagnosis of PEM fuel cell. And this topic is very actual since now PEM fuel cell doesn't have any diagnosis system on board of their controller. So we suggested the solution of that is based on DC-DC converter, which is very advanced. The agenda of presentation, I will give a brief introduction of the consortium, then we will review some motivation and objective of the topic and concept and achievements, and then some results of the project. So let's see the partnership. The partnership is a good balance between some among industries and SME and academia and research center in Europe. We had also some cooperation with other university and research centers such as Aalborg University and the Fraunhofer Institute. The project put together innovation from the industry, from the research, and then the objective is to have a system that can be ready for the market through the implementation of very basic equipment and component in an industrial environment. The main motivation is the need of advanced diagnosis tool for the fuel cell in order to improve the lifetime, in order to have information on the state of the health, and to reduce some empiricism that today we can find into the diagnosis of fuel cell, in order to have quantitative feedback and to mitigate the degradation of the system, in order to detect malfunctioning in the system during its life. So we want to move from something that is very empiric, just based on the experience of the operator, such as in this case, you see what's going on there, and then you try to apply some solution, but it's everything is very empirical. Our approach is to have some information, and then through an automatic system try to find what is the best solution for the system. So the main objective is to use this electrochemical impedance spectroscopy technique, which is something that is now applied basically in the lab. So it's a very complicated system that requires some complicated measurements. And then the idea is to move the EIS from very controlled environment, which is very expensive and very clean. And then we want to move this in a system which is unattended, so no operator, is very contaminated and should be very cheap. Then the idea is to develop a DC-DC converter. This was the basic idea, in order to measure directly in the stack the impedance, which is reported here as the results of this measurement. And then this has been applied on the low temperature and high temperature fuel cell. And the idea was to get some indicators from the spectrum of the cell. So the targets the main target is to have quantitative assessment of the status of the fuel cell, and then of course to have some further information in terms of monitoring and failure prediction, and are reported such as the forecast the forecast of the lifetime. Future application could be also the control, advanced control, also to improve the dynamic response and fault recovery, and so on. So the challenges we consider for this project goes from research and development to the industrial application. I'm not going to review all this detail, but the main challenge was to have this EIS on board. As I said, move the diagnosis, the EIS diagnosis from the lab scale to the field, to the environment in which the system is working. And then we approached several of these changes we solved, because this is the last year of the project, so the results are very interesting. And the final is at industrial level. It's the possibility to exploit the project outcomes for industrialization in order to have this board, as I will show later, on the system itself. Then review the concept and diagnosis scheme. So the advantage of EIS is that the EIS bring all the information about the cell in unique measures, which is the spectrum of the impedance of the fuel cell. So the idea was to measure only one information, and then to exploit from this information all the data that are embedded in it. And then the idea is to have the status of the system while the system is running on field. This is another complicated matter, because in the lab you have an environment which is controlled, and here and in the lab you know when the load is applied, while on the real system you don't know whether the load is applied or the system is in standby in some other condition. And the objective, as I said, is to have a deeper comprehension of the relationship among causes and effects related to the fuel cell status. So the basic concept is this: we have the low temperature and high temperature fuel cell, and then we have in this case is a low voltage DC-DC converter and a high voltage DC-DC converter that were basically developed for the purpose of this project. This is the board. This is the heart of the project, because in this board, which I'll show you later, is 10 centimeter by 10 centimeter, we embedded all the hardware and the software in order to perform the EIS. So we move from very big and expensive component in the lab, at lab scale, to very small and cheap component that can be manufactured very easily. And also even more miniaturized, as I'll show later. Then we get the EIS here. You see the spectrum, the spectra for several operating conditions. And then the idea is to take this information and then to have some further elaboration with the several techniques. In this case, it is a model-based approach, and here there are two different approaches based on AMPHIS and on fuzzy logics, and then to derive some indicators in order to have some information in order to have the diagnosis and to know exactly the status of the fuel cell. The scheme is like that. So this is a complete system. We have the balance of plant, the fuel cell stack, and then several components that will be shown in a minute. Here we have the two low temperature and high temperature. Here we have this is the high voltage DC-DC converter, or in other case the low voltage DC-DC converter. This is the component. Here we have the controller of this converter, and here we put this board that controls the converter in order to inject the signal and to perturb the behavior of the fuel cell, and then to measure the impedance. And then we derive the impedance, as I said before. This is the classical shape. And then here we have the output of the elaboration after the EIS, and from this we derived the diagnosis. The achievement, as I said before, here we have the lab environment. This is the AFER lab, and this is the big component that is used for the EIS in the lab. While here you see the small board that has been developed within the project in order to perform the EIS. This is the high voltage converter, and this is the fuel cell that was provided by Danterm, which is one of the partners. This board was developed by Bitron, is a company very active in the electronic industrial component. This was developed by Sirtem, and then we will review later the other partners that developed the analysis performed on the EIS. Just as I said before, this is the small board. You see is a 10 centimeter by 10 centimeters, and then you can compare with the dimension of this equipment. Of course, we achieve several results according to the description work that was submitted to the Commission and approved by the Commission. So we characterize the low temperature fuel cell, we select also the high temperature, and then we perform, thanks to cooperation with the Aalborg University, the fuel cell in standby within very cold environment in a climate chamber. We also achieve the design and the manufacturing of the high voltage and low voltage DC-DC converter, the ES board, the spectrum analysis, and the two converters that were assembled and tested here. And also now the low voltage converter is still under testing for the final results. Then we developed the model and knowledge-based diagnosis algorithm, as I said before, in order to infer from the ES spectrum. We implemented it, as you will see later in the results. And then we developed other methodologies and techniques in order to analyze the output of the spectrum. As a first consideration, this is a scheme. This is the standard scheme of the DBX 2000 system that was provided by Danterm, and this is the basic configuration. In order to implement on board the ES, a small change was introduced in the configuration, so it was split the feeding of the electricity to the balance of plant in order to the component of the balance of plant, in order to avoid the influence of the balance of plant on the measurement that is taken afterward with the EIS. Then we characterize the system in the lab. So these are the spectra that were acquired on both systems in the standard and modified configuration. So the changes in the configuration did not change the shape of the spectra. And then this is, as I said, taken from the laboratory equipment. And these here are the two spectra at 20, 25, and 5 amps in the load, and were taken with this equipment, with the board that was developed. And as you will see, the shape is not very far from the shape that were shown before. So this was very good results and important achievement for our results. So we were able to reproduce the same shape of the spectra even with this small component. One of the algorithm is a model-based algorithm. Then we measure from the fuel cell. We measure with this system the spectrum, which is shown here, and then we identify this spectrum with a model-based approach. So we have a model which is a circuit, equivalent circuit here, and then we derive some information that, as I'll show later, will give us some information on the health of the system that may be in faulty condition, or we can get some information in the monitoring in order to have the status of the system at that moment. And here you see with the black circles, we see the experimental data that were taken from the EAS board. And then we have the fitting in this red and green curves, the fitting that has been achieved with our model. In that case, we can consider the parameter identified with the model as main information that can be used for the diagnosis. So the main idea is to see how the parameters identified change with respect to the standard condition. In this case, we can infer on the status of the system as is shown here. For example, this is a normal condition. These are some curves that relates the membrane resistance with respect to the current densities according to the changes into the humidity level inside the membrane itself. So we are in normal condition. This is the region in which we expect to get the resistance. In this case, we have three conditions in which the membrane resistance change moves away from the best humidified condition, and so we can say from this information that for sure we may have either drying or more water than it is needed from the with respect to the lambda equal 14, which is the best operating condition. So this is just an example shown here. Then the algorithm has been implemented. This is our diagnostic algorithm, and it is interfaced with the Dantherm system and the Bitron system hardware. So we have integrated all together, and then we can have the results. So this is the configuration that you can find on the real system once it will be implemented at the end of the project. This is just a screenshot of the application. This is the monitoring system from Dantherm. And then below, we added some more information that has derived from our algorithm that has been embedded in the controller. And then we can infer on the status of the system, having some information on the status of the cell. This is another technique that has been developed by Université de France Comté. Our colleagues developed a diagnosis based on fuzzy logic. So we have a clustering in several conditions as a function of the status of the system in either faulty or nominal condition. And then after that, decision can be taken about the status of the state of health of the fuel cell. For example, this is the shape of the fuzzy rules that were implemented, and we can discriminate among healthy and severe drying or situation that may be out of range, or medium drying on the other condition according to the clustering. So the actual measure is taken, and then we see whether it is in a healthy state. So if it fall in this region, or here, or somewhere else. This is a set of experiments performed by our colleague at UFC. And the important point is that technique was applied on another fuel cell that was not considered within the project at the beginning, in order to show the reliability of the technique on another cell. And this is also the interface of UFC in order to have the, you see, this is the acquisition, the data acquired here, the measurement, and then the point that is added to the clusters, and then the diagnosis is available after the analysis and the numerical data treatment with the fuzzy logic. What are the next steps? We are going to, in the future of this project, we are going to apply in order to apply to the Commission, or at least at the industrial level. We want to move from TRL 3 or 4 to TRL 5 or 6, which is the technology readiness level. So we move from very basic research to applied research in order to have field testing for several systems, to also to detect other faults like contamination, poisoning, or mechanical damages that can appear in the, can occur in the fuel cell itself, in order to improve the state of health monitoring for degradation and in case lifetime prediction. And one of the applications of these techniques, thanks to the cooperation with Aalborg University, is the end-of-line quality of the stack before the assembly. This is a very important point in order to guarantee the quality of the stack before the final assembly. And then we also apply this technique to solid oxide fuel cell, because the technique is very general. So from a methodological point of view, the application to solid oxide requires something like another project like the one we have, the one I have just presented, but it's just a matter, I will say, of time. Because now we know exactly in which direction we should move. So the application of solid oxide, I will say, is almost straightforward. And then the outcome of our monitoring system could be also to implement, could be also the application in the area of advanced control. So we can monitor the system, and then we can supply some information to the control algorithm in order to improve the performance of the fuel cell. So we had also some in the area of dissemination and publication. We had some journal articles, some international conferences, and other papers that were written by the partner of the project. And we involved also in this project several PhD students. One was part of a joint PhD project with the University of France Comté, and several students at undergraduate and graduate students. So we have a good dissemination of the results of the project. Thank you for your attention.
Thank you very much, Mr. Pianese, for this informative and interesting presentation here on stage. So now it's your turn. Are there any questions here from you, from the audience? Not yet, I think. Just raise your hand. I will pick you up with the microphone. So if not, and if there's some coming later on your mind, or you like to discuss more directly to him, just don't hesitate and come to the booth. It's here at the group exhibit, Hydrogen Fuel Cells and Batteries, and the booth number is C35. C35 here at the group exhibit. I think you will welcome everybody.
Thank you.
Thank you. Thank you. It's your applause again. So, I proudly announce our last presentation here after a short break from 5 minutes. And the topic we will talk about now is extreme hybrid power sources. And they will be presented from the Chief Executive Officer, Paolo Faracas, from Genport Power Solutions.